So here we are at chapter 16. Only about 5 chapters to go in this workbook, and we're kind of switching gears in that we're going to mix in a little geometry with what we've been talking about as far as radicals and exponentials, expressions, and whatnot. And first thing that probably jumps out at you is we have a formula. Okay, and so what we have here that's similar to previous chapters is we have an x squared and a b squared, and so what we're looking at on the left hand side is the sum of two squares. Alright, and that ends up being equal to another square. Okay, and the title of this chapter is the Pythagorean Theorem and its converse, and this has to do with triangles, specifically a right triangle. And so the theorem states, if a triangle is a right triangle, then the sum of the areas of the squares on the sides. And so it's referring to this left hand side in our formula, a squared and b squared, we have the sum. So, and as you know, if you have a perfect square, then why does it mention the areas? Well, say we had a square that had one side labeled with an A. Well, if this is a perfect square, then all of the other sides have the same lengths. Alright, and there's two sort of characteristics that we can calculate from this. We could say the perimeter is 4 times A. Alright, but that really doesn't apply here. What I'm trying to home in on here are the areas, and the area of a square, in this case an area of a square with a dimension of A would be length times width, A squared. Okay, so I'll write out the little formula to the side, but both length and width are the same dimension or the same length, so A squared, and so that's why they refer to these parts as the areas of squares. Okay, it says is equal, okay, to the area of the square on the hypotenuse. So the hypotenuse, it's sort of the diagonal feature of a right triangle, and it happens to be the longest side of a right triangle. Okay, so you're just being told that here, but one thing you could do if you weren't totally convinced, or maybe you need to be reconvinced that this is true, then you could take your workbook. You only paid $20 for it, so you could cut out this little diagram here, and you could sort of label the sides of your triangle as A, B, and the hypotenuse C. And you see here in between these squares we have a right triangle. Okay, A and B are what we refer to as the legs. They meet to form this 90-degree angle, and so that's what this box here in this corner means. This is a right angle. Alright, so one right angle for a triangle, and you've got a right triangle. Okay, C is the hypotenuse, and B and A are legs. Okay, what you can do if, as we said, we construct squares out of the lengths of the sides of this triangle, then this is going to be our B triangle. Okay, so all the sides of this triangle measure B. Likewise, all the sides of the square. All the sides of this square measure A, and then all the sides of this large square measure C. Now, if you cut this out, okay, and you place this bigger square this bigger square as far as the legs go. If you place this square, I'll highlight it in red, inside of the biggest square, then you'll probably, I'm just gonna sketch this and try to do my best. You'll probably get something that looks like this. And if you cut out this smaller one, what you can do is fill in what's left by cutting strips out of the smaller square. And you should cut out strips to where it completely fills up what's left once you put a squared inside of c squared. So in other words, the area of this square, b squared, plus the area of this other squared, a squared, is going to give you the area of this larger square here, c squared. So this, whatever's left, that area is going to be taken up by strips from the b squared. Okay. So kind of a fun little activity that you can do with this chapter to prove the Pythagorean theorem. This next page gives you a little bit about Pythagoras, the guy who came up with the theorem. A bunch of interesting information there. But I'm just going to skip to this next page where we start to talk about the converse. So specifically the converse of the Pythagorean theorem. So you can see in the definition that they've given us here, on one hand, if we have a particular statement like the Pythagorean theorem where we said if right triangle then it obeys our formula, the sides. Alright, so if this, then that. So it's real easy to construct the converse. We just simply reverse the roles of the if-then statement, and instead we write if we find some links that satisfy this formula, then the links form a right triangle. Okay, so this is our original statement, and this is the converse of that statement. So, and that's exactly how the converse of the Pythagorean theorem reads. If we start with a triangle, or if we start with some numbers, some links that where you add the squares and it equals the square of the third side, then we have a right triangle. Okay. It's just the reverse of the theorem. And it turns out that it's also true. Okay. And so you could probably come up with your own statements, but not necessarily the converse is always going to be true. So let me think. For instance, we could make a statement: if you can see the sun, then it is daytime. Okay, so this is our original statement, and the converse would simply be if it is daytime, then you can see the sun. Which isn't necessarily true. Okay, it could be daytime and the sky's cloudy and you can't actually see the sun. So converse isn't necessarily always true. But in the case of Pythagorean Theorem, it is true. And we're going to use that to work some of the problems coming up on the next few pages. Okay, so here we have a little example in reference to a college basketball court. They wanted us to find the diagonal, the length of the diagonal. And the diagonal is just simply the imaginary line that passes from one corner to the opposite corner of this rectangle. And of course you probably know that a basketball court forms a large rectangular shape. Well, they told us that the length was 94 feet and the width was 50. And so as with a lot of these problems, you're playing the game, find the right triangle. And so once we draw the diagonal through the basketball court, you can actually pick out two different right triangles. But since we constructed these two triangles by simply chopping a rectangle in half, these end up being equal triangles, so it doesn't really matter which one you use. If you look, they both obviously have right angles. Okay, so they're both right triangles. And then if we started with a rectangle, then the dimensions are going to be the same in as far as the legs. So if the two legs are the same and we have the same angle between those two sides, then these triangles are going to be identical. Well, you only need one of them, and you see that in order to answer the question, we've labeled our hypotenuse in either case as x, and you square the two sides, 94 squared, 50 squared, and that equals the hypotenuse squared. In this case, we used x instead of c. We square the two numbers, and then when we get here, in order to get rid of the squared part, because we just want x, we don't want this 2 here for an exponent, we do the opposite operation, which is a square root to both sides, and we get 106.5 feet. Alright, so if you got a situation and you're missing a length, and you can make you can find a right triangle, then you can apply Pythagorean Theorem. Example 1, we have basically a problem that's identical to the last one. We just have different numbers, and this is about as good as I can do in the way of a rectangle. Wish these were straighter, but our dimensions are 84 and 50. This is a high school basketball court. Okay, so college is a little bit longer, I guess. Wants us to find the diagonal, which is the length from one corner to the opposite corner. I'll label this as C, and it says express our answer in exact and approximate form, which usually means to say exact, it's in fraction form, and approximate just means we divide the numbers from the fraction and get a decimal number, and then we round it. So draw and label a picture. That's exactly what we did here. If you wanted to, you could put a little box in this corner to show that it's 90 degrees. And at this point, we found our right triangle. Okay, here is our right triangle outlined in blue. So we simply need to apply the formula square of the sides added together equals the square of the hypotenuse. Our legs are 50 and 84, so we have a 50 squared and an 84 squared equals c squared. The 50 squared is a 2500 And let's see, 84 times 84 gives us 7,056. We add those, 7056 plus 2,500. We get 955.6. Okay, 9556 equals c squared. Okay, so we added these first. Now we want to get rid of this squared part, so we take the square root. Alright, so back over here to my calculator. Just hit the square root button. We get 97.75. We were told to round to the nearest tenth. So the square root of 9556 is 97.8 rounded to the nearest tenth. This square root knocks out this exponent 2, and so c is now by itself, and here is our answer. This square root 9556, that would be our exact. So this is approximate, and then if you were asked to give an exact solution, you would just say c equals square root of 9,556. Alright, so 556 exact. And in this case, we didn't get a fraction. We got a radical expression. So this is another instance of an exact answer. Okay, this isn't a perfect square inside, so when you take the square root of it, you're going to get an irrational number that never repeats and never ends, so you can't write it as a fraction. It's just another instance of an exact answer. So on to example 2. It says we have a triangle. It doesn't say we have a right one, but it tells us that this triangle has lengths of its sides 5, 12, and 13. And the question is it a right triangle? So what we're doing here is we're applying the converse of the Pythagorean theorem. What we're going to do first is check the numbers to see if they satisfy the formula. Okay, a squared plus b squared equals c squared, and automatically I picked the biggest number to be our hypotenuse, because if these do form a right triangle, then the longest side is going to be the hypotenuse. So 13 squared gives us a 169, 5 squared gives us a 25, and then 12 squared is 144. So if we pull up our calculator and we add 144 plus 25, we do get 69, so that checks out. So in other words, we can construct a triangle, a right triangle, with these dimensions. Alright, so here's our right angle with the box in the corner, and our sides measure 5, 12, and 13. Alright, 3, if the length of the sides of the triangle are square root of 5, 2 square root of 11, and 7, is the triangle a right triangle? When you have radicals, you may want to evaluate the radicals so that you can compare them to the numbers that do not have radicals. Just looking at this, you may think that 7 is the biggest number, but it would surprise you as to how close 2 square root of 11 comes to being the hypotenuse, or the supposed hypotenuse. So what we need to do is take our calculator, and we have 11 and we want to calculate the square root, and then we want to multiply it by 2. We get, of course, this is an irrational number. These digits never end, so we have to sort around it, but you can see that 2 times the square root of 11 is approximately 6.63, okay, which is still less than 7, but it came close to winning the spot for the hypotenuse. Alright, so just double check your radicals before you just put the numbers in the formula. Make sure you're putting them in the right place. But at this point, that's exactly what we're going to do. We're going to take our formula a squared plus b squared equals c squared, and we're going to put in square root of 5 and 2 square root of 11 as our legs, and then we're going to write 7 as our hypotenuse. So we square a square root, and the inside just falls out. The 2 is on the outside of the radical here, so a 2 squared would give us a 4, and then when we squared the square root of 11, we would just have the 11. So here on the right side, 7 squared is a 49, and back on the left we have a 5 plus a 44, which does give us a 49. So these numbers that we were given obey this formula. Therefore, we can say that these dimensions do form a right triangle. Square root of 5, 2 square root of 11, and then this side would measure, it's the hypotenuse, it would measure 7. Alright, example 4. The idea is the same. We're going to apply the formula a squared plus b squared equals c squared once we lay down the dimensions of our triangle. And here they're sort of switching it up on us. They're going to throw in a variable instead of just giving us the numbers outright. This problem tells us that we have legs of x and x plus 3. And the hypotenuse is 15. Alright. So we dump these dimensions, the legs, x plus 3 and x, in the spots of A or B, doesn't matter which one. As long as you don't put x or x plus 3 in the place of C. C is reserved for the 15, which we were just told that the hypotenuse is 15. And we automatically know that it's a right triangle also. So we're going to use our sides in the formula. We end up squaring some variables. We have some parentheses here. When you place x plus 3, substitute it into the formula for b, you have to square it, so it's the square of a binomial. You can't just square the x and 3 individually. Turns out to give us x squared and a 6x plus a 9. 15 squared on the right side gives us a 225. And you can see now that we're going to end up with a quadratic equation, a little more challenging. We have 2x squareds and with this being a quadratic equation, we do want to put it in standard form so that we can solve it. And so this 225 needs to move to the left side along with all of the other terms. And now we have standard form with 0 on the right, a minus 216, our 6x, and a 2x squared. Now, looking at this 2 here, you should be thinking that, hey, we may need to do the AC method. But it turns out that the coefficients of the other terms are also divisible by 2. So what we'll do is we'll just use the greatest common factor method and take that 2 out. We end up with the x squared plus 3x minus 108. And this 2 can either sit there for the rest of the equation solving, or if you wanted to, we could just take both sides of our equation in its current form and sort of throw the 2 away into the 0. If we divide both sides by 2, the 2 cancels on the left, and then a 0 divided by 2 is just going to end up giving us another 0. So it sort of gets absorbed into the 0 there. You can't do that when this greatest common factor contains an x. Alright. This part inside the parentheses is what we keep. So I'll go over here. Here's what we're left with. We want to concentrate on factoring the trinomial on the left. And if you play around with the numbers, you will end up with a minus 9 and a plus 12. Okay, so that's minus. Alright. At this point, you break it apart into 2 separate equations. An x plus 12 equals 0 and an x minus 9 equals 0. This equation gives us a negative 12, and this one gives us a plus 9. Now, both of these are probably solutions to the original equation. We could check it, but I'm not going to do that. I just want to point out that x represents a physical dimension of this triangle, and we do not measure things in terms of negative numbers. So what we're going to do is we are going to throw away that negative 12. It's a solution to the equation, but not our application problem. And the one that we're going to use is our x equals 9. Okay, so in other words, this bottom side, according to the way I drew my picture, this bottom side equals 9. This second leg over here would be x, which we found to be 9, and then add 3 to it. It would end up being 12. Okay, so here's all 3 sides: 12, 9, and 15. The next problem, we have a ladder leaning against a building. You don't have to make your picture too complicated, but it does help sometimes to just draw a picture. Here's the ground, and we're just assuming that the builders knew what they were doing when they built this building, and it goes straight up and the ground is perfectly flat. If that's the case, then this angle that the building, the wall of the building and the ground, they meet at a 90-degree angle. So here is our right triangle. Okay, the ladder, the ground, and the wall form a right triangle. And let's see, what did they tell us about this, the dimensions? Okay, ladder's 24 foot, so it's obviously our slanted, our longest side. It's going to be our hypotenuse. So C equals 24. The bottom of the ladder, right here, is 8 feet from the base, or in other words, the bottom of the building. So this is where it's talking about. This is said to measure 8 feet. Okay. Now they want to know how far up the side of this building the ladder goes. Okay, ladder's 24 feet, but it's leaning against the building, so it doesn't exactly go from the base up the side of the building 24 feet. It's a little shorter than 24. So we want to find this side, and we apply our formula: a squared plus b squared equals c squared. Alright, the c is our ladder, and either a or b is going to be our 8, the distance from the bottom to the bottom of the building, the bottom of the ladder. And then a is going to be the one that's missing. Okay, how far up the side of the building the ladder goes. 8 squared is a 64, and 24 squared gives us 576. We want to get the a squared isolated before we take the square root, so we subtract 64 from both sides. We end up with a 512. And now to get the a by itself, we take the square root. So with my calculator, I'll type 512 and take the square root, and we see we get about 22.6. Our 8 and 24 were given in terms of feet, so this 22.6 is also going to be in units of feet. So here is the answer that we were looking for. Alright, appears when I scanned the workbook, I left the previous page out. But what you're going to see on that page is a general situation where we have a line segment on a coordinate plane. So we have the y and we have the x-axis, and somewhere we have a line segment. Okay, that line segment is drawn between two different points. It's just a straight line. Now what you're told is on one hand, one coordinate is just in general x1 and y1, and then the second point is going to be labeled with the 2 subscript. Alright, what you do in this situation to determine the length of this line segment, or you could say the distance between these 2 points, would be to imagine forming a right triangle out of this line segment, with this segment being the hypotenuse. So we would just simply draw a horizontal line and a vertical line connecting these 2 points. Alright, so what I want to do at this point, and you were given a formula on the previous page, but what I'm trying to do here is just point out to you that this is just sort of a the Pythagorean Theorem with a little bit of makeup on it. Let's suppose that we had the points 2 and 3, and then the coordinates of this point were maybe let's say 6 and I don't know, 5. Okay, now this, if we drew this line, this bottom side of our imaginary triangle, perfectly flat, and then we drew this side, the vertical one, perfectly straight up and down, then these 2 sides would form a right angle. And with this slanted side included, we have a right triangle. and we know that the sides obey Pythagorean Theorem. A squared plus b squared equals c squared. Now, with these numbers, we can calculate the dimensions of this triangle. Let's look at x first. Okay, how long is this side here on the bottom? Well, if we drop down from the endpoints of the side, then just by reading the coordinates, we can say that this point with respect to the x-axis starts at 2. This other point, the point that forms the end of this bottom side, it stops at x equals 6. Okay, so with this side being perfectly parallel to the x-axis, we can say that its length is just simply the difference between these two numbers. 6 minus 2 equals 4. What we've calculated there is x2 minus x1. Okay, this was the second x coordinate, this was the first one, and we subtracted the two. So what we can do with this 4 is put it in the place of one of these legs, a or b. So we have a 4 squared. Now we'll do the same thing with the y. Okay, y is a vertical side, so if we want to find its length, all we have to do is trace it back to the y-axis, read the y coordinates, the bottom one's 3, the top one's 5, and take the difference of them, 5 minus 3. We get 2. So b is a 2, and we square it in our formula. Well, if we were to just give general names to 5 and 3, we would call 5 y2 and 3 y1. The second y coordinate, the first y coordinate. We subtracted the 2. Alright, now armed with the numbers, we can just go over here and figure out this distance that we're wanting to know. And of course I'm using different numbers, but I'm trying to sort of explain to you the reasoning behind the formula from the previous page. With the numbers, we can say we have 16 plus 4, and then that gives us 20, and then we just simply take the square root, and we see that c is the square root of 20. Now, where did the formula come from on the previous page? We can use Pythagorean Theorem to calculate this distance. Well, the formula just simply came from, instead of taking the numbers, we take these expressions and we put them in the place of a and b. Alright, so if we do that, what do we end up with? For either a or b, we end up with an x squared minus x1 squared plus a y2 minus y1 squared equals c squared. Okay, if we want to know this distance, if we want to know the measure of the hypotenuse, then the c squared, if we want to solve for c, we have to take the square root of both sides. The right hand side just ends up being c, or in the case of the previous page, a d, the distance that we want to know. And then you see this formula with all the variables and all the subscripts. But what they're telling you is to just simply subtract the x's, subtract the y's, square each one, add it, and take the square root. Okay, and that'll give you the distance between any 2 points. Alright, so let's do that real quick. X1 is negative 2, Y1 equals 5, X2 equals 3, and Y2 equals negative 6. It does not matter which one you call 1 or 2. I could switch these subscripts. What we do is we take the difference of the y's, -6 minus the other y. We take and we square it, take the difference of the x's, 3 minus this minus 2, so we get a double negative. We square that. We add those two squares together and we take the square root. This is going to give us our distance. So now all we have to do is add all this up. This is a -11 squared. This other piece is a 5 squared. Minus minus is a +2. 3 plus 5, or 3 plus 2 is 5. Alright, we'll bring down our square root, and we have a 121 plus a 25. That ends up being the square root of, let's see, we have a 6, we have a 4, 146, and that's our distance. This is the exact solution, and then they want us to come up with an approximate one. So we just simply pull out our calculator, type 146, and then hit the square root button, and we get approximately 12.08. Example 7, I'll label this x1 or x1 and y1, and then x2 and y2. We're going to take the differences and then we're going to square them. So we take the two x's, -2, and subtract the other one, -3, and then we take the y's and do the same thing. -1 minus a -4, and then we add them together and take the square root. This first set of parentheses ends up being a -5, and we square it. Second set ends up being a 3, and we square it. We get the square root of a 25 plus a 9, which is the square root of 34. So this is our exact answer, and we'll pull up our calculator. 34 and the square root, approximately 5.8. So this is exact, and this is approximate. Okay, skipped a little bit. Oh, there it is. 3 types of triangles, since we're talking about the Pythagorean Theorem. Scalene means that no sides have the same length. Isosceles, 2 sides, and equilateral mean that all 3 sides are equal. And we're referring to the lengths of the sides, not the angles. Now for equilateral triangle, the angles end up, they are all equal, but we're focusing on the sides. So we'll go to the next page and see exactly what they want us to do with that information. Okay, what they tell us is that we have a triangle and it's plotted on a coordinate plane, and these are the 3 points of the triangle. They want us to determine whether it's scalene, isosceles, or equilateral. So first we'll sort of sketch it. The first point is at a 2, 2. So +2 + 2 for y and x. Then we have a 1 and a minus 3, so down 3. Here is another point of the triangle. And then a third point at negative 3 and up 1. So 1, 2, 3, and then up 1. Not the best sketch, but it gives us some idea as to what the triangle is going to look like. Now this kind of looks like an equilateral, but we don't want to just go by our picture because it's not that good of a picture. What we're going to do is we're going to calculate, and I'm going to label my points, and this will be helpful. Label my points A. Well, let's not use A. Let's not do that, because we've got A squared, B squared, and C squared. So I'll use, let's see, X, Y, and Z. So we've got X point, we've got Y point, and then we have Z. Alright, so there's 3 sides here. There's 3 distances that we need to calculate. We need to calculate distance X to Y, which is the same thing as the distance from Y to X. Okay. We need to calculate the distance from Z to Y, and then we need to calculate the distance from Z to X. Alright. Our first 2 points that we're going to consider are Y and X. So we've got 2, 2, and 1, negative 3. We'll subtract the Y's first, then the X's, square both of them, and then take the square root. We end up with the square root of, let's see, 5 squared plus 1 squared, which is the square root of 26. Okay, so off to the side, we'll keep up with that square root of 26. I need to make some room here. And now we'll compute the distance between point Z and Y. So these 2 points, coordinates, alright, what goes in the parentheses? The difference between the Y and the difference between the X. So for the Y's we have a 1 minus a minus 3, and then for the X's we have a negative 3 minus a 1. We add the 2 together. This works out to be 4 squared plus a negative 4 squared, which gives us the square root of 32. And now for our last distance. Okay, so at this point it's definitely not equilateral because these 2 sides weren't equal. It either has to be isosceles or scalene. So we got a square root and then squares inside that are added together, and in the parentheses we put the differences between the coordinates. So I'll go up here and we'll point out which coordinates we're going to use. That would be 2, 2, and then negative 3, 1. Okay, we take the difference of the x's, minus 3, minus 2, the difference of the y's, 1, minus 2. Doesn't matter which one comes first or second. And then we write negative 5 squared plus 1 squared, and that gives us a side that is equal to the first side. So in other words, we ended up with 2 sides equal. this one and that one. The third side's different. So what kind of triangle are we dealing with? That would be isosceles. Oh, it's a hard word to spell, but isosceles triangle. Okay, so quite a bit of work, but same formula in each case. You have to calculate the distance between three different points. Alright, and this brings us to our last example, example 9. It says, when tested over this material, Logan said that a triangle whose side lengths measured 3, 4, and 5 inches respectively was not a right triangle because 9 squared plus 16 squared does not equal 25 squared. If he was correct, explain why you agree with him. If he was wrong, what errors did he make? Well, let's see here. We have sides 3, 4, and 5. These are the numbers that we're supposed to check with our formula. With 3, 4, and 5, 5 being the longest side, it has to be our hypotenuse. So we'll square 3 and we get 9. We'll square 4 and we get 16. We'll square 5 and we get 25. And then 9 plus 16 equals 25. Okay, so I would say that Logan, he squared the numbers and then he squared them again. Okay, if we want to check this, we could write down what Logan had. And let's see. A 16 squared is a 256, and a 25 squared is a 625. And 9 squared is 81. So if we add these two sides, Logan is correct in saying they are not equal. But he put in the wrong numbers. Okay, these aren't equal, but he used the wrong numbers. He used 9, 16, and 25. He should have used 3, 4, and 5 in combination with the formula. And in that case, if he had done that, the two sides end up being equal, which tells you that the triangle was a right triangle. Is a right triangle. Alright, so I hope you learned a little bit. At this point, you may want to try some practice problems at the back of the chapter, or get on Alex and see if you can complete your homework. If you got any questions, feel free to come by my office. Thanks for watching.